All right, so what we're looking at today, we're on day 4 here, the binomial theorem. What we're hoping to do is to develop a formula that would come up if I have any two terms. We call this a binomial, and it's to the power of some exponent n. We want to be able to come up with a way to quickly answer what that is in expanded form. So we're going to start that by looking at the following combinations. Remember that in bracket form here, bracket 0, 0, this is referring to a combination type question. It's the same thing as saying we have 0 items. How many ways are there to choose 0 items from 0 items? Well, I can choose nothing. I can choose nothing. So there's one way to do that. This is a situation where I have one item and I want to know how many ways can I choose nothing from that. Well, I can choose 0, or I can choose one item once, so that's 1. As I continue down, we can see our pattern emerging. Each time the number of items that I can choose is increasing by 1. So I started with 0 items to choose, 1 item to choose. Now I have 2 items to choose from, and I want to know how many ways can I choose 0, nothing from 2. I could do that one way. How many ways can I choose 1 item from 2? Well, I could either choose item 1 or item 2. So that means there's 2 ways I can do that. Or how many ways can I choose both items? Well, I can choose 1 and 2. I can choose both of them one way. As I continue down, you'll start to see that we're really seeing a pattern here. Now we're choosing from 3 items, and I can either choose 0 items, 1 item, 2 item, or 3 items. And these are the answers to our combination questions. So what is this really giving us? You'll notice that these numbers, 1, 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3. This is, of course, just our Pascal's triangle that we've seen before. So what do we notice about the value of these combinations? They are equal to the values in Pascal's triangle. All right, so we're trying to draw a correlation between combinations and Pascal's triangle. So if we assume that this pattern continues, the idea is that when n is 0, our numerical form up at the top we saw has a value of 1, and we write that in combination form as 0, choose 0. That's for the 0th row. On the first row, well, the numerical form becomes 1 and 1. We write that in combination form as 1, choose 0, or 1, choose 1. Continuing down to the second row, the numbers from Pascal's triangle generate a 1, a 2, and a 1. Or in combination terms, that's 2, choose 0, 2, choose 1, 2, choose 2. Going to row 3, the numbers in Pascal's triangle are 1, 3, 3, and 1, or 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. And in the fourth column, we got the numbers are 1, 4, 6, 4, and 1. Combination form, 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. So we're just drawing this. We want to really recognize that Pascal's triangle, the numbers that we've looked at, we can also, it's exactly equivalent to writing this out in a combination form, using combination notation. The fifth row, our numbers are 1, 5, 10, 10, 5, and 1. I can just confirm that, right? 4 plus 6 is my 10, 6 plus 4 is 10, 4 plus 1 is 5, right? My numbers are fine. So on the fifth row, that means I have 5 elements to choose from, right? If I have 5 elements to choose from, I can either choose 0 items from that 5, 1 item from the 5, 2 from the 5, 3 from the 5, 4 from the 5, or 5 from the 5. And this is saying that 5 choose 3 is equal to 10. And 5 choose 2 is equal to 10. We saw that yesterday when the terms add up to each other. When the 2 plus 3 adds up to the 5, we saw that these were symmetrical, that they had the same values. We had the values of 10 and 10. That was on yesterday's note. Okay, let's continue on to page 2. So this is going to... Again, we're trying to come up with a way to express expansions of binomials. So in this page, we're asked to expand each of the binomials below using FOIL. Remember that FOIL stands for the first two brackets, or first two terms in the bracket, the outside two, the inside two, and then the last two. All right, so we're going to be using FOIL to expand our binomials. So in this particular case, first of all, anything to the power of 0 is just 1. So the coefficient, well, there's just the value 1. So the coefficient is, of course, 1. When I have a plus b to the power of 1, that is simply a plus b. It's just the power of 1. Here's where we're going to be using our FOIL. A plus b squared, remember that's the same as saying a plus b times a plus b. Our FOIL says we multiply the first two, that's a and a, gives me a squared. The outside two, which is a and b, a times b gives me a plus b. And then the inside two, b and a, the outside two are a and b, that gives me ab. And then the inside two, b and a is the same as ab. We can see that ab plus ab simplifies to 2ab. And then the last two would be my b times b, or b squared. So what are the coefficients in front of this? In front of the a squared, it's implied that we have a number 1. In front of the ab is a 2, and in front of the b squared, again, we don't write it, but it's implied that there's a 1. So our coefficients become 1, 2, and 1. When I expand a plus b cubed, from yesterday's note, you should have practiced doing these expansions. That gives us a cubed. Again, I'll write the 1a cubed plus 3a squared b plus 3ab squared plus b cubed. Again, that's implied that there's a 1 there. Our coefficients become 1, 3, 3, and 1. 1, 3, 3, and 1. Continuing with the power of 4, or you can start to see maybe where we're going here. Pascal's triangle, the fourth row, is the same as taking a plus b to the power of 4. That gives me 1a4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. That's 1b to the fourth. So our coefficients are 1, 4, 6, 4, and 1. 1, 4, 6, 4, and 1. And we'll continue on to the fifth one. A plus b to the fifth, which is the fifth row, is a to the fifth. That's 1a to the fifth, plus 5a to the fourth b, plus 10a to the third b squared, plus 10a squared b cubed, plus 5a b to the fourth, plus, again, 1b to the fifth. Our coefficients are 1, 5, 10, 10, 5, and 1. So we should be recognizing that these coefficients are, of course, simply Pascal's triangle. So can we predict the expansion of a plus b to the sixth? How can we do it? Well, the expansion of a plus b to the n has n plus 1 terms. Is that true? Here we have to the power of 5. It's the fifth row. We've got 1, 2, 3, 4, 5, 6 terms. Right? So we have 6 terms on the fifth row. We got 1 extra term. On the third row, we have 1, 2, 3, 4 terms. So we have 1 more term than the row. So if we are in row n, or the exponent is 10, that means we have n plus 1 terms. Therefore, the expansion of a plus b to the 6 has 6 plus 1, or 7 terms.